Hi everyone, this is my second video on deep members. If you watched my first video, you are able to identify what's a deep member, what's a slender member, and you should be able to distinguish these regions. In this second video, I'm going to talk about two related concepts. The first one is shear span to depth ratio that quantifies how deep the member is. I'm going to do one example. We are going to find shear span to depth ratio, and I'm going to give you some thresholds, and I will tell you below this threshold, it is a deep member. Above a certain threshold, it is a slender member. Also, I will give you a range. It's a transition zone. In that zone, you can analyze it as if it was a slender member. Plus, I'm going to show you the capacity gain depending on shear span to depth ratio. Deep members are more efficient. There is a common misconception with regards to deep members because we are not teaching deep members in undergraduate education. Practitioners as well as students tend to think incorrectly that deep members are something to be avoided. The reality is that deep members are more efficient than slender members. They have more shear capacities, and they are more desirable members. I'm going to show you how much additional shear capacity you are going to get from a deep member as compared to a slender member. I'm going to show you a chart which you can download and you can use it as a reference. You calculate your shear span to depth ratio and then you see the percentage difference. It's going to give you some range to have an expectation because at the end of the analysis, you can use that chart to do a sanity check. All right, that's enough talking. Let's get into work. Let's start with the first example. I will call this example number 3 because I covered example 1 and 2 in the first video. Again, let's just do the same analogy. Let's say 2.5. Excellent. Very good. 25 millimeter. So from this, I would go 25, which is here. And from point load, I would go 25, which overlaps. This is a really significantly deep region. So it is almost 1-to-1 aspect ratio. This should really start from here. There is really no slender region. So you have to use deep beam analysis methods to design this span. If you look at this one, you would have a slender region. A little bit though, but still you can do your check shear capacity moment calculations for that region. Slender region. This is B region. The left shear span, deep member. Let's highlight the shear span concept. What's shear span? So the shear span here would be this distance between 2 point loads. Call this A. Look at A to D ratio is similar to 1.0. This is a very deep member. I'm just showing you how to identify the intensity. So one is a rather deep member. If you look at the right shear span, it is a slender member. Again, I'm calling this slender member, but any typical slender member will have deep regions. That's the same situation, but that means you have some B region at least to do your checks. A2 would be this distance, 67 millimeters. D was 25. Of course, in your structure, you would have the real numbers. Here, I'm just showing you a conceptual example. 2.7 is a slender member. I will come to a conclusion if you want to formulate this. A to D ratio, shear span to effective depth ratio. If A to D is larger than 2.5, it's a slender member. If A to D ratio is 7.5, it is a really slender member. The larger the ratio, the more slender the member is. The smaller the ratio, you see an example here, the deeper the member is. If this ratio is smaller than 2, it is a deep member. You might also ask what happens in between. You can call this transition zone if you wish. use slender analysis method. So this graphical representation always works. You don't have to do this ratio, but with this ratio, I would like to give you some more understanding about this topic in order for you to qualify, is it a really deep member, is it a really slender member, or is it in the transition zone? So transition zone, it's fine to use slender analysis method. Let's look at one of my journal papers. This is a paper about how to analyze deep members. I would like to show you a plot to better clarify shear span to depth ratios. It shows you shear span to depth ratio, which is on the horizontal axis. Utilization ratio is on the vertical axis. If the utilization ratio is 1, the member is at capacity. So in other words, the smaller the ratio, the less utilized the member is, meaning that it has more reserve capacity. So you want ratio to be smaller. If you look at sectional method compared with the strut-and-tie method, so the proposed methodology is a strut-and-tie method, which we proposed in this paper, utilization ratios significantly diverge after 2.5. So shear span to depth ratio smaller than 2.5, divergence start. Larger than 2.5, you can see they really merge to each other. There is no significant difference in between. 2 and 2.5, you can consider this as a transition zone, but any ratio less than 2, there is going to be significant discrepancy in terms of your calculations. You shouldn't be using your sectional method for analyzing anything less than span to depth ratio 2, but we did use it in this study to demonstrate what happens if you use it. You would return significant errors. That error will increase as shear span to depth ratio decreases. In the example, we got really deep members with a ratio of 1. You can see the capacity predictions almost twice the numbers if you use sectional method. Download this paper. It's available on my website, and you can refer to this in terms of how much mistake you should expect if you end up using sectional method for deep members, which you shouldn't really use it. As I showed you in the plot, you would get significantly larger capacities if you use the proper method for deep members, which is the strut-and-tie method or finite element analysis method. I came back to this example because there's something which I would like to show you. In a slender region, reinforcement stresses will change depending on the location. The stress will diminish, and it would be 0 at the simply supported point. For that reason, we cut reinforcement without checking the development length. Because reinforcement is not needed, you can cut it at a simply supported point. However, for deep regions, it is not that situation. Deep regions have a constant reinforcement stress. So whatever the maximum stress is for your region, it is going to be constant over the shear span. So if you look at stress contours, let's say you did a finite element, you will see this almost the same. For that reason, development is very important. If you don't develop the bar at the support, you wouldn't benefit the increased capacity of a deep member, and your member will simply act as if it was a slender member. So you would lose the efficiency which comes with deep members. Keep that in mind. Whenever you have a deep member, reinforcement must be anchored at supports, meaning that it has to be developed properly even if you have a simply supported point. One way to do this is to use a hook. If you have enough overhang, you can just simply develop this, but more than often you might need a hook to develop the bar. This is really important. I should really write it. To benefit from the deep beam action, reinforcing bars must be properly developed at all nodal points. All right, that's it from me today. Thank you very much for your attention. I hope I was able to answer a couple of questions in your mind. If you find the content useful, please don't forget to subscribe and give a thumbs up to this video. Thanks again for your attention, and I'll see you in the next video. Bye for now.